Welcome to this demonstration of our DIAS-ITA research, adapting AI systems to recognise new patterns of distributed activity. I'm Alan Priest from Cardiff University, and my co-presenters are Dave Brains from IBM Research Europe and Mark Roj-Villamala from Cardiff. Our collaborators on this research are IBM US, Imperial and UCLA, as well as ARL and DSTL. Here's the bottom line up front. Military operations typically involve working with partners to resolve rapidly evolving situations where adversaries are adapting their tactics, techniques and procedures, and the behaviour of the civilian population is changing. In this context, military information processing systems need to be able to recognise, in near real time, significant patterns of activity which are distributed in time and space, exploiting diverse AI assets available from coalition partners. Our scientific contribution comprises a suite of integrated techniques which enable patterns to be recognised where there is insufficient time or data to train a deep learning AI model. Humans can directly inject new knowledge or hypotheses about patterns of activity. AI models can be trained faster, with significantly reduced need for training data and improved detection accuracy compared to pure deep learning approaches. Our architecture benefits from being loosely coupled, built from open source software in an open architecture. The Coalition AI services can run on edge-of-network devices, thus being suitable for tactical sensor systems. The research seeks to enable defence to adopt AI systems which learn and adapt at the pace of the fight, to ensure tempo of understanding and action is not overmatched by adversaries. We demonstrate the research in the context of monitoring a rapidly evolving situation in the NATO Anglova urban setting via diverse AI assets processing multimodal sense data with management of situational uncertainty. We focus on 4 AI services, each showcasing particular DIAS research technologies. Firstly, a CCTV processing service owned by Anglovan local law enforcement, located outside a popular nightclub frequented by members of Anglova's Capulet community, detects an active shooter event via deep neural network processing of audio-visual data running on an edge device. To build trust, the service is able to provide multimodal explanations for its outputs with associated uncertainty. Secondly, a social media monitor service owned by the US coalition partner and located in cyberspace, detects threats of violence directed against the Capulet community via deep neural network natural language processing on Twitter data. Again, the service can offer appropriate explanations and is equipped to provide uncertainty awareness. The Capulet Plaza Listener service, owned by the UK coalition partner and located in a busy public plaza in the Capulet part of town, processes audio streams via a neurosymbolic AI architecture, able to detect an IED explosion when trained on a relatively small set of training data. Finally, a situation monitor service, owned by the UK coalition partner and located in cyberspace, performs probabilistic logic programming, with rules injected by subject matter experts to detect that the 3 preceding events constitute a situation of interest, i.e., escalating violence directed against the Capulet population of Anglova. I'll now hand over to Dave Brains, who will introduce you to our situational understanding software environment.
This demo shows a situational understanding example based on the collaboration between human and machine agents in a human-agent knowledge fusion environment. The purpose of this environment is a place where human and machine agents can rapidly build and exchange knowledge through tellability, which is informing new information, or explainability, which is going deeper into explanations of why information exists or has been added. Through capabilities such as this, we provide the opportunity for human-machine teams to be defined and configured in near real time in response to situations as they arise, rather than assuming that they can be predefined in advance. The separate demo named Cognisketch, enabling rapidly formed human-agent coalition teams through extensible information exchange, covers this environment in more detail should you be interested in the underlying research principles that have informed its construction. The palette on the left-hand side provides a set of capabilities and services that can be used, customized or extended and shared as needed for each use case. For example, here we have the standard core entity types as well as specific additional extensions to support Coalition Situation Understanding, or CSU. We'll be seeing each of these 4 CSU types created and interconnected as the story progresses. We have a service, which is the AI machine services that have been deployed into this environment, usually in a distributed setting onto the sensors themselves, but they could also be run remotely in cloud infrastructure. We have the explanations, which is any additional information from the service which provides some form of explanation for any events that are detected. We have uncertainties, which in real systems recognize that all observations and inferences come with uncertainty information, which is essential in terms of any downstream inferences or human assessment. And finally, events. These are the events that can be detected by services in the environment, and these are specialized into a number of concrete types, based on the capabilities of the services, in this case explosion, violence, shooting, and situations. Finally, there are numerous ways to interact with the information in this environment. For example, if we navigate to the map view, we can see that we have a couple of sensors located on the map, an audio sensor on Capulet Plaza, and a CCTV camera here outside the Capulet Club on Anglover Boulevard, and this is within the Anglover city setting, within the NATO vignette. There are a number of core views, and it is easy to extend with custom views, palettes, and AI agents as needed. Embedded into this environment are the services that were described in the introduction. We have the Capulet Club CCTV service, the Situation Monitor service, as shown here, which is generic and trying to make sense of the situation in the city, the Capulet Plaza Listener service, and the Media Monitor service. Two of these services are specifically located based on the sensors they are connected to, and the AI processing is located directly on these sensors at the edge of the network. The other services are not located in a specific geolocation, but operate in cyberspace with the AI processing running in appropriate locations within the Coalition cloud. So, okay, let's see what's happening in Anglover based on the services we have deployed. All the services are running, and we can use this environment to get more information about them and see what's happening as they create events. So we can see here that the Capulet Club CCTV service has observed an active shooter situation in front of a nightclub that is deep into Capulet controlled area, one of the two leading factions in the city. The explanation for the event contains links to the relevant raw input from the sensor, which in this case is the CCTV video and audio feed. This can be seen on the canvas as the SAVER, Selective Audio Visual Relevance, explanation, which takes the form of an attention highlight video showing the audio and visual relevance of the scene. Full details of the SAVER research can be seen in the corresponding demo titled Real-Time Explainable Artificial Intelligence, Time Series and Multimodal Data. This event has been assessed to be likely some confidence. This is a natural language representation of a subjective logic opinion that distinguishes the amount of belief, disbelief, and epistemic uncertainty in the truth of a given proposition. Each event comes with a source uncertainty assessment that can be modified upon ingestion into the platform. The source uncertainty here has been discounted at 80% because the sensor and service are run by the local Anglovan authorities, whereas the coalition user maintaining situational understanding is from the UK. This can be seen by the small decorator icon to the left of the service that indicates this is a local Anglovan authority service, and other decorators for US and UK can be seen elsewhere on different services. This information is all available in the graph, but is hidden by default to ensure the users are not overwhelmed but can navigate to any relevant information as needed. The analyst has seen this shooting event and has a hypothesis of escalating violence against the Capulet population. There is no time or data to retrain the Situation Monitor service, but we can readily modify the rules to inject the new hypothesis in near real time. The analyst, therefore, would like to upgrade the Situation Monitor service to be particularly focused on any discussion on social media that may indicate increasing unrest, specifically by looking for early indication of violence towards Capulets. This is a technical update and would likely be made by an operator user who has responsibility for maintaining the services, but this environment can also support the input of higher level information from which such code as this can be generated. After reviewing the current configuration, the user decides to extend the rules and link this into the new configuration. This could either be done by extending the existing configuration rule or by creating a new additional rule as shown here. The rule is now live and has updated the running service accordingly. As time passes, the Media Monitor Service, an evidential deep learning equipped asset of the Coalition using a machine learning model able to express epistemic uncertainty when facing unseen data, signals a credible, likely some confidence threat to Capulets. Other DIAS research into attention-based natural language processing explanation methods highlights in red the threatening features of the tweet shown here. Due to the earlier rule change, the Situation Monitor Service is also triggered, creating a situation based on both the active shooter event and the threats of violence from social media, both of which are targeting the Capulet community. Initially, the uncertainty is likely with low confidence, with the rationale noting that this is computed from component events, which are indicated via the is explained by links from the active shooter and threats of violence events. The rules continue to run and the situation will be updated as any new related events are detected, with the certainty being revised accordingly. Finally, an explosion event is detected based on the Capulet Plaza listener service. As with all detected events, a link to the explanation is shown along with the original audio should the analysts wish to assess the event for themselves. This AI service is very confident, generating a very likely certain classification for this event. And since this listener service is run by the UK Coalition partner, there is no modification to this certainty. The new explosion event is also linked to the unfolding situation due to the spatio-temporal proximity, and the certainty for the situation is updated accordingly. I will now hand over to Mark, who will talk about some of the scientific implementation of the Capulet Plaza listener service.
The listener service is implemented using DeepPropSep, a hybrid neurosymbolic architecture. DeepPropSep combines a neural network and a logic layer, which allows us to train the system using far less data than neural-only approaches. This diagram shows the implementation of DeepPropSep used in the demo. The first step is to split the input audio into 1-second segments. Each of these segments is then passed through VGGish, a state-of-the-art feature extractor. VGGish outputs a feature vector, which is then fed into a neural network. AudioNN in the diagram. AudioNN will output a classification of which sounds happen in the given second of audio. Based on this classification, the logic layer will detect the situations of interest defined in the rules. DeepPropSep allows experts to manually define the conditions for a situation of interest. However, in this case, we have used FastLAS to learn the rules through inductive logic programming. This has allowed us to train DeepPropSep in an end-to-end manner without the necessity of an expert to define the rules. In the diagram, we can see some of the rules generated by FastLAS. Despite being automatically generated, these rules are still understandable by humans with a logic programming background. For instance, the first rule defines that a single ID attack will occur if an explosion sound is detected for at least 2 seconds without being interrupted by complete silence. This is the rule that detected the explosion for this demo. In order to train the system, we first obtained the rules using FastLAS. This was done using a very small dataset with different situations of interest we wanted to detect. Then, the whole system can be trained in an end-to-end manner. In order to do this, the training audio must be provided to the system, which will then use the neural network and rules to predict if a situation of interest is occurring. This will then be compared to the ground truth and used to generate a gradient for backpropagation. Using the PropLook, the logic layer is made differentiable, which allows us to train the neural network to detect the sounds that appear in the audio.
Thanks, Mark and Dave, for presenting the details of our approach. To summarise, here's the bottom line again. In this demonstration, we've shown how our research enables patterns of events to be recognised where there is insufficient time or data to train a deep learning AI model. We highlighted 2 key capabilities. Humans can inject new knowledge or hypotheses about patterns of activity through addition of new rules. AI models can be trained faster, with significantly reduced need for training data and improved detection accuracy compared to pure deep learning approaches. We also highlighted loose coupling of hybrid types of AI systems in an open architecture, and how the resulting applications are able to run on edge-of-network devices, so are suitable for tactical sensor systems. We demonstrated AI services operating in multiple domains, physical and cyber, on a variety of data modalities with awareness of situational uncertainty. We offer these technologies as a means to enable defence to adopt AI systems able to learn and adapt at the pace of the fight. Further information and open source code for the technologies featured in this demonstration can be found at the DIAS ITA GitHub site via the links shown here.